Welcome to Launching a WebAssembly Cloud with Fermyon and Nomad. I'm Matt Butcher. I'm the CEO of Fermyon. I've been around the container ecosystem for a long time. I'm one of the original creators of Helm and of a number of other kind of cloud native applications. I'm the co-creator of the Illustrated Children's Guide to Kubernetes. These days, though, I work primarily with WebAssembly, and I'm really excited about what we're going to talk about today because this is really the first time I've gotten to talk about some of the operational parts of WebAssembly in the Fermyon Cloud. So WebAssembly, we think, is going to be the next wave of cloud computing, and I'm going to talk a lot about that today. But just recently, we launched a platform, and I want to start by telling a little bit of a story about that launch. On October 24th, we launched the Fermyon Cloud. It was a hosted service. In essence, Fermyon Cloud is sort of like, it's a platform as a service. You can think of it as like Heroku, where developers upload their own applications. Backed by and orchestrated by Nomad, it hosts WebAssembly microservices and web applications. So at first, we saw about 100 users in the first week. Then it was 200. Then it was 300. And soon, Fermyon Cloud was hosting hundreds of applications for hundreds of users. It's time for us to have one of those frank conversations about the size of our Nomad cluster. We'd provisioned 8 extra large virtual machines in AWS, and most of them were doing nothing. So while our customers and apps were going up and up and up, it was time to talk about scaling down. Okay, now that's a peculiar story, right? Because most of the time, what we think of is when you start with a fairly modestly sized cluster, and then you start to see a pretty good pickup from users and applications, we would expect to have to grow the cluster, especially when we're starting with only something like 8 nodes. Instead, we're now talking about scaling it down because we're essentially wasting electricity. What makes this possible? Well, that's where WebAssembly comes in. So if you were to ask for a textbook definition of WebAssembly, it would go something like this. WebAssembly defines a portable, size and load time efficient format and an execution model specifically designed to serve as a compilation target for the web. That's the definition that Luke Wagner gave when he first wrote his first blog post about WebAssembly. But what that means is essentially this. WebAssembly is a standard that defines a way that you can compile different languages like Rust and C or Java, C#, Python, Ruby into a bytecode format that can be executed inside your browser side by side with JavaScript. Now, this original idea was sometimes you want to program in a language other than JavaScript when you're writing web applications. Wouldn't it be cool if you could take a C thing and compile it and have JavaScript call functions inside of C? This was actually accomplished with great aplomb by Figma, who has a giant set of C++ libraries that they've compiled to WebAssembly and used inside of the Figma offering to do certain things very, very quickly. Figma, of course, being a graphical design tool, being able to do mathematical computation very quickly is an exciting thing for them. Now, we took a look at this, well, actually, even before that. We were not coming at this from a web browser problem, right? In fact, we had nothing really to do with web browsers at all. We were looking at a different problem and looking for a solution to that problem. Here's the problem we were looking at. My career, I've been around long enough to remember running everything in a data center, right? And we would install a particular version of an operating system on top of a bare metal instance, and then we would install our application into that operating system. So really everything from kernel to operating system up to application code, really starting from bare metal and moving up from there, was something that we managed, right? And this was a difficult way of operating things, often introduced conflict between developers and the platform engineering, but something changed in the ecosystem around us. And when I first noticed it, when I was at HP Cloud and starting to work on OpenStack, it blew my mind, right? Because up until that time, I had really thought of operating system and physical hardware as having a one-to-one relationship. You installed exactly one operating system on your hardware. You could really only run one operating system at a time, even if you were doing something like multi-booting or dual booting. Along come virtual machines, and that fundamental assumption I had made just went by the wayside, right? The hypervisor made it possible to run multiple operating systems simultaneously on the same piece of hardware. Now, still, we were managing everything from the kernel and the drivers up through the operating system libraries and utilities and file systems and on into our application code. But essentially, we no longer had to run our own hardware. In fact, we could bundle things up and ship it off to someone else so that they could run it on their hardware, and never again did I have to worry about something going out in the rack. So virtual machines were cool, and I was really excited about them. Then along came another technology, and this was the container, right? Made famous by Docker, though I know others had variations of this. Docker really built a set of tools that made it possible to easily build and then operate containers. Now, containers started at a slightly higher abstraction layer. Instead of bringing my own kernel and bringing my own drivers, my application would just split kernel time with any other applications that were running in their containers on the same piece of hardware. So I had a little bit less to worry about, right? Still packaged up much of the OS, all the core libraries I needed, the file system, the utilities, and so on, and then just dropped my application on top. And these images were much smaller. So this is the situation that my team found ourselves in a couple of years ago. We were working in Kubernetes. Now, we were used to the two different types of computing, virtual machines and containers. Now, virtual machines are sort of like the heavyweight class, the workhorse of the cloud, and they did a lot of really good things for us. But they take a long time to start up. Sometimes they take minutes to start up, and they're kind of a burden to be able to manage. Now, containers are lighter weight, and they start up faster, but still they were taking seconds to start up. And we were looking at all kinds of new technologies that were coming out, particularly under the umbrella of serverless. And functions as a service in particular was very exciting to us. But trying to handle problems like the scale to zero problem, which we'll talk about quite a bit during this talk, we could not figure out how to do that with containers. We couldn't figure out how to do it with VMs. We made some progress, but never did we really find a satisfactory solution. And this kind of sent us back to the drawing board to say, wait a minute, okay, so if virtual machines are the heavyweight class of computing, and containers starting up at around seconds are sort of like the middleweight class of cloud computing, what if there's a third class of cloud computing, like kind of lightweight kind of cloud computing that would be the engine that drove things like serverless functions? So we started looking around. Is there a thing that we can use that would run in the cloud and provide us a bunch of those kinds of security isolation benefits we get with containers and virtual machines, cross-language, cross-platform, cross-architecture support, and also really, really fast startup times? The technology we discovered that seemed to fit the bill was WebAssembly. So we started saying, all right, well, there's got to be a way to take WebAssembly out of the web browser and run it on the cloud. Turned out we were not the only people to think that way. The Bytecode Alliance had already been building a reference implementation of a WebAssembly runtime outside of the browser. It's called WASMtime, and it's the runtime that we've used really ever since our first experimentation. So with this kind of outside of the browser runtime, we could begin building cloud services based on this. And so we began experimenting. And what we really wanted to do was figure out a way to run serverless functions using this third class of cloud computing. Why serverless functions? Well, because we had talked to a lot of developers and we kept hearing the same story. And the story went something like this. Writing a serverless function is delightful because all I have to do is create a little function and start working immediately on the business logic that I care about. Contrast that with the way I've been writing microservices, which is first step, download a bunch of dependencies, start up an HTTP server, write a routing table, manage the SSL certificates, manage process interaction, and then I can start to work on the business logic. So I have a huge pile of dependencies, and I have a big giant piece of boilerplate code, and all of that has to be in place before I can begin writing my business logic. So developers were telling us they didn't like that model. They liked the serverless model where I could just dive right in and start writing the code that I cared about. But there were a couple things about serverless functions they didn't like. First one was vendor lock-in. They felt like, well, if I buy into Lambda, I'm really stuck on Lambda for all of eternity, right? The second one was the design decisions always seemed to be dictated to them by the individual cloud providers. You could do X on Lambda, you could do Y on Azure Functions, and you were just waiting for them to provide and meet the feature set that you needed. Now, beyond that came the real frustrating points for people. The applications were hard to debug, they were hard to package, they were hard to maintain, operators had very little say into how they operated, and they always felt sort of disjointed from the rest of the applications. They're running a bunch of stuff in Kubernetes, and then way over here on the side is a couple of Lambda functions that aren't operated, aren't managed the same way as the rest of the stuff, and that just never sat well with developers. They like the model, but the operational part of it was just a huge headache to them. So what we heard from that is, if we can figure out how to solve that problem better, then we will make a lot of people happy. And WebAssembly seemed to give us the key ingredient to solving that problem better. So when we started Fermyon about a year ago in November of 2021, we decided we really wanted to build 3 things in order. The first one was a developer-oriented tool that would allow developers to get started right away. In 3 commands, they should be able to go from a blinking cursor to having something to test. Spin new to create the application, spin build to compile it to WebAssembly, and then spin deploy to push it somewhere. That was the second thing we needed to build. We needed to build a place where they could push their code and then run it in production. That was the first version of this was Fermyon Platform. Now, Fermyon Platform is an open source, self-hosted platform that can execute WebAssembly modules, particularly for HTTP. We have other cases too, like Redis listeners, but HTTP was really our core case for microservices and web applications. Now, we built Fermyon Platform for a couple of reasons. The first one is we wanted to make sure that there was an open source reference for how we saw these things running in the cloud. Second one, which was honestly really more important for us, is that we wanted to be able to run our own applications on a service, and Fermyon Platform was our first cut at this. So Fermyon.com runs on a version of the Fermyon Platform. The Finicky Whiskers game, which we'll see in just a moment, runs on a version of the Fermyon Platform. And really all the Fermyon Platform is, at the end of the day, is a Terraform installer that you can point at your cloud provider or tendency of choice, bare metal or DigitalOcean or whatever you want, right? And you can be running a Nomad, Consul, Vault cluster with all the tools necessary, spins runtime and a dashboard and things like that to execute your own deploy and execute your own WebAssembly-based applications. So that was step 2. Step 3 was that we really wanted to build the sort of like giant version of Fermyon Platform. We wanted to build and host Fermyon Cloud, where any developer could deploy any of their applications right away without having to think about infrastructure at all. So really, it should be as easy as spin new to create a program, spin build to compile it, and spin deploy to push it up into Fermyon Cloud, where they can run it without having to think about infrastructure at all. A lot of what we're going to talk about in just a moment will be Fermyon Cloud and how we built it and the cool things that are coming out of it as we've started to see how it works. But before we get there, I wanted to give you a quick demonstration of how fast WebAssembly is. So this is a game called Finicky Whiskers. It's a little cat game. You can go play it at finickiwhiskers.com. And the idea is that this cat, Slats, keeps changing her mind about what she wants to eat. She's based on one of our colleagues' cats. So one moment she wants beef and you're clicking beef as fast as you can to feed her. And the next moment she wants vegetables and you're clicking vegetables as fast as you can to feed her. Now, every time you click a button, you are sending a request to Fermyon that is starting a WebAssembly module, running it to completion, and coming back. And as you go, the faster you play the game, the more WebAssembly applications you're spinning up, running to completion, and shutting down on the other side. So when we get a score of around 117, we're actually invoking grand total somewhere around 300 individual instances of a WebAssembly application. Now, what should strike you about that is, wow, I can't even imagine starting up a couple of Docker containers and running them to completion in the 30-second window you play the game, and yet we can start, run to completion, and stop 300 of these when they're written in WebAssembly. So the Finicky Whiskers game is built with 9 different WebAssembly microservices, each one handling a different feature of that game. Some of them are attached to the buttons, some are attached to the timers, but they're all written in using this function, serverless function model. We also have a Redis application, Redis instance that's running inside of a container. And all of this is being orchestrated by Nomad, and there's a Nomad cluster on the back end. Again, this was all built with Fermyon Platform. And then the runtime there is Fermyon Spin. We built everything in Spin. There's a Spin runtime embedded in the Fermyon Platform that's executing all of these things. So Finicky Whiskers is a really good illustration of the performance profile of WebAssembly and how we can orchestrate that and run that in production. But for the rest of this talk, I really want to focus not so much on Spin and on platform, but on the Fermyon Cloud that we just launched, because we're learning a lot about what WebAssembly looks like in a production environment as it scales out when we look at the cloud. I'm excited about this because this is actually the first time I've ever gotten to talk in public about this. It's only been about a month since we first launched this, and now we're starting to learn our first lessons about how to operate WebAssembly in a Nomad cluster at a pretty good scale and increasing in scale as we go. So the topology looks sort of roughly like this. We've got a control plane, we've got a data plane. The control plane is exactly what you would expect in a HashiCorp deploy talk, right? We're running Nomad, Consul, Vault. That should say Vault, not Nomad at the bottom there. We're running Nomad, Consul, and Vault. We're running them in a kind of production grade configuration as we learned to do from the documentation at developer.hashicorp.com. And that's really all the data plane has in it, is just kind of the usual suspects. And a control plane. So our data plane has currently, as I mentioned at the beginning, about 8 different workers. I don't know how many purple boxes I put there because I just kept copying and pasting till it looked like a lot, but 8 is what we are currently running as we start talking about scaling down. Each of those workers is definitely running 2 workloads. Everyone is definitely running an instance of the Traeffik proxy. That's an HTTP proxy that we use to route traffic into particular applications. The second one it's definitely running is LHC. So LHC is a little bit of a pun there, right? Fermyon is a small particle. Fermions have spin. So spin, the tool, is also named after a geeky physics joke. LHC is the Large Hadron Collider in Switzerland. We thought it would be funny to name our big giant instance of spin LHC. So LHC is actually more like Containerd. It's sort of a big environment where you can schedule hundreds and thousands of WebAssembly modules to run on top of that one execution context. So Traeffik and LHC are running on every one of our Nomad workers. Now we also have a couple of containerized workloads. We've got a package repository called Bindle that holds all of the WebAssembly applications. Databases tend to be a better fit for longer running processes and consequently are better managed as containers. Fermyon API server is a similar one. It's the always on API server that we could actually rewrite in WebAssembly, but our first shot at it was not. And so we continue to run that as a container as well. So we got a couple instances of the repo, couple instances of the API server running on our Nomad cluster, and then every single worker instance has both Traeffik and LHC on it. Now, when it comes to the flow of data through this application, this is kind of how it goes. So let's start with the red line. I'm an application developer. I'm writing my first Fermyon application. I type in spin new, create my local application, type in spin build it to a WebAssembly binary. Now I type spin deploy. Locally, my application gets packaged up. The WebAssembly file, a couple of supporting components, all of that gets packaged up into what we call a bindle, and that gets pushed off to the Fermyon Cloud. Now, the first thing that it hits logically is it's going to get routed through a Traeffik proxy and sent to the Fermyon API server, which is going to check credentials, do all of that stuff, and then create a new instance of the application. This is going to take the binary, it's going to load it into the package repository, and then it's going to schedule a job with the Nomad cluster and say, hey, can you schedule this WebAssembly module out to one or more of the LHC instances running out there? Nomad's going to do that. When LHC gets the request, it's going to fetch the package out of the repository, unpack it, and load it into its runtime. It's not going to start it, though. So now here, just pause for a moment. So now we've got WebAssembly modules that can be running on any number of or can be loaded on any number of worker nodes in our cluster. But none of them are running. None of them will run until a request comes in, because there's no point in wasting compute time running something that's not handling any requests. We'll come back to that because that is sort of like the real magic that makes WebAssembly so much better for these kinds of serverless environments. Pause on that though, and let's talk about an incoming user request. So now I've deployed my application. It's gone to like foo.fermyon.com or something like that, right? A user request comes in for an HTTP GET request for foo.fermyon.com slash whatever, right? This gray line sort of traces that path. So the request comes in to a Traeffik proxy. The proxy knows where all the different WebAssembly applications should be served from currently, and it'll route it to one of the workers, and the worker will, the LHC instance there will say, okay, I need to start up an instance of this, watch it handle the request, and then shut it down when it's done. Now, starting up a WebAssembly module takes under 1 millisecond. So in a blink of an eye, your application is up and running and handling the request and returning a response. If it's sub 1 millisecond, there's no point in running it all the time, right? Because we can just start it up and stop it. It's far more efficient to start it up, run it, and stop it. So this is great for that kind of serverless or microservice that's stateless or stores its state in a reliable stateful storage like Redis or like a database. So that's kind of the overview of this. Now let's start to contrast this with another traditional way of running microservices and see where the differences arise. So let's talk Kubernetes. Right, Kubernetes, one of the more popular ways to schedule and run container workloads. An extra large Kubernetes, an extra large virtual machine running in AWS can run around 30 to 40 containers in Kubernetes. Now, when I write an application destined for Kubernetes, a microservice, I, as the developer, write this application, compile it, containerize it, and then push the container up and push up a deployment manifest. Now, typically, Kubernetes gets this deployment manifest and says, okay, so I'm going to run somewhere around 3 instances. That's considered best practice, is to start at 3 and scale up from there. So my one microservice gets run on 3 different nodes on my Kubernetes cluster. That means it's provisioning enough resources on each of these nodes to run all the time. And it is indeed running all the time. So when I'm at peak load, I've got 3 instances. When load is dropped to 0, because it's 2 in the morning, I still have 3 instances, and it's consuming all the resources it needs to keep a full HTTP server running and everything loaded into memory and everything operating as normal. Now, imagine my little microservice begins to get popular. It's time to scale up, right? Hacker News sends a whole bunch of traffic, or, I've got an e-commerce site and Black Friday or Singles Day is rolling around. I might have to scale up from 3 to 5, or from 5 to 7, or from 7 even to something like 9. Now, again, what that means if I hit 9 is that I have 9 instances of my application running at all times in my cluster, ideally spread around the entire cluster. At 2 a.m., I'm running 9 instances. At peak load, I'm running 9 instances, right? That means that I'm essentially in a situation called over-provisioning, where I have to provision for my peak load, not for my average load, and definitely not for my minimal load. And the reason we have to do this with systems like Kubernetes is, going back a couple of slides, right? Because containers are slow to start. They take seconds, 12 to 15 seconds to start up, and no user is going to wait for 12 seconds for their request to start being handled. Consequently, we have to run in this over-provisioned state. Now, with WebAssembly, we've been able to go the opposite direction. Instead of over-provisioning, we don't even have to right-size the provisioning. We can under-provision. And what I mean by that is we can actually install apps very aggressively, because we know that when they can start up and shut down in this like millisecond window, then I can start, run, and stop one application and start, stop, run another application. There's no point in leaving anything running all the time. And consequently, we know that it is not the case that all of these applications are going to be running at the same time. So we can actually resource for only a percentage of the applications that are actually installed on the cluster. And then we can scale up those and down those individual ones without necessarily having to scale up and down our cluster, and without having to worry that everybody's going to be executing everything all of the time, which essentially is a core concern that Kubernetes has to address. In fact, what we've seen in practice is that probably less than 1% of the applications are running concurrently. Right. So what we're learning, and why we're talking about scaling back, is that resource utilization is actually much lower than we had anticipated. The concurrency thing is actually playing to our benefit. Now, this graph here gives you an idea of that, right? We know that currently we're running somewhere in the neighborhood of, say, around 100 applications per instance. And I'm not totally sure what the exact number is. We know from our testing that we can easily run 900 applications per extra large virtual machine. We suspect that it's actually much, much higher than that, but we're taking our baby steps toward that. So if our cluster size is 5, right, we have 5 worker nodes, then we know we can run 5 times 900 applications. If the cluster size is 8, we can, 8 times 9, okay? So you get the idea. Now, here's what it actually looks like CPU utilization-wise on a particular Nomad worker. So you can see when we were in our pre-launch moment, just before October 24th, we were doing a little bit of load testing. You can see a couple of peaks here and there as we did those tests. Then we went live on October 24th. Here and there, we saw a couple of customers running load tests, which kind of shot CPU usage up. But most of the time, the CPU usage is sitting very, very, very low. Now, here's the thing. If you take a look at the scale on the left-hand side, the highest peak on there is 3.2% of the CPU. The highest line on here is 4% of the CPU. Our CPUs are basically sitting idle even though we have 100 applications on there and they're getting executed. That's about the time we realized that this provisioning strategy for under-provisioning WebAssembly modules is actually pretty legit. We actually think it's working even better. So if our CPU utilization is sitting under 1% on average, and our memory usage sits at about a constant plateau of right in the area of 8 to 9 gig, usually right around 8, we don't see a lot of spikes on memory. We preload a lot of stuff at the beginning, and then it stays at a pretty constant 8 gig. So if that's the case, right, then we don't need 8 extra large virtual machines. So we have begun talking about, well, maybe it's time to start scaling down and saving on the electricity bill a little bit. That's why it's been so exciting as we've begun this process of running things inside of Fermyon Cloud. WebAssembly and Nomad have just proven to be a great combination. And as I've said before, we're using Nomad to be able to schedule Docker containers for things like the Bindle repository, or in the Finicky Whiskers game for the Redis instance. And yet we've also been able to write a fairly small driver and execute WebAssembly tasks side by side with these containerized tasks in a Nomad cluster. So very excited to get to share this. There's a sense in which when you put together a presentation like this and submit it in your call for papers early, you're never sure whether things are going to come out. And I didn't know whether by this point I'd be saying, we scaled from 8 to 12 or 8 to 16 or whatever. So it has been just a lot of fun to see that a lot of our initial theses about how WebAssembly modules would execute were even shown to be maybe too pessimistic, and that we can get a little more optimistic as we kind of see this under-provisioning strategy play out. So if you want to get started with Fermyon Cloud or with Fermyon Platform, you can head to fermyon.com/cloud, walk through the quick start guide there, and have something up and running in 2 minutes or less. If you want to play our cat game, that's finickiwhiskers.com. You too can experience the speed of WebAssembly modules as you try and feed slats to cats and generate some load on our servers. If you really want to go straight to the code though, github.com/Fermyon is a great place to go, /Fermyon/platform, github.com/Fermyon/installer will take you straight to that installer so that you can install it on the cloud provider or bare metal option of your choice and try it out for yourself. With that, thank you very much. I'm happy to answer any questions.